So, refer to this problem. There is a spring in its natural state, unelongated state, and there is a mass attached to one end of the spring and is originally at rest. At one end of the spring, there is a variable force F applied upwards, and the system is released in a gravitational force field. It is found that the mass m at an instant of time t has an acceleration given by g minus alpha t. The value of alpha is given to be 1 meter per second cube. We want to be able to find the velocity of the end p as a function of time. This is what the problem is all about. Now, if I have knowledge of the acceleration of the mass m as a function of time, then very clearly I can find the velocity of the mass m as a function of time. Yes or no? Right? V prime is the velocity of the mass m at an instant of time t. Now, this a could be written as ddt of v prime. So, this a is ddt of v prime. Yes or no? Right? Now, this would give us an opportunity to at least obtain the velocity of this mass at various instants of time. So, very clearly, dv prime is g minus t dt. Right? Now, when you integrate at t equal to 0, v prime was 0. At t equal to t, let's say v prime became some v prime. Right? Now, this very clearly means that v prime, the velocity of the mass m at t equal to t, is like gt minus t square by 2. Gt minus t square by 2. How about it? Right? One thing. Now, my objective is to find the velocity of the end p, v, as a function of time. Look at the free body diagram of the mass m. Look at the free body diagram of the mass m at an instant t. What are the various forces acting on the mass m? We will assume that the elongation of the spring at an instant of time t is x. X is a function of time, the elongation in the spring. So, at this instant of time, the spring is elongated by an amount x over and above its natural length. What are the forces acting on the mass m? There is mg downwards, there is kx upwards. Yes or no? Right? Now, given this, let me write down the equation of motion of this mass m. The equation of motion of this mass m is mg minus kx, the net downward force, right? The spring force is kx upwards, as you can see. That must be equal to mass into acceleration given as a function of time. The problem offers to us the acceleration of the mass as a function of time, g minus t. So, mg minus kx would be m into a, which is like m into g minus t. Yes or no? Right? M into g minus t. Now, very clearly, mg gets cancelled from both sides. Mg gets cancelled from both sides. And if mg gets cancelled from both sides, I end up getting kx equal to mt. Kx equal to mt. This is what we get. Yes or no? Now, if I differentiate both sides with respect to time now, see, mg gets cancelled, so minus kx is minus mt, so kx is mt. Now, if I differentiate both sides with respect to time, I end up getting k dx dt, rate at which elongation changes, equals m. K dx dt, dx dt is what? Rate at which elongation is changing. That's equal to m. Yes or no? Right? Good. Which means, now, would you want to believe this is an instant of time t and the spring of force constant k has already received an elongation x. Now, the rate at which elongation changes would be the relative velocity between p and q. Yes or no? pq is the length. see, if this is P, which has an upward velocity V, which is what we are seeking to find. This is Q, which has a downward velocity V prime, right? What is the relative velocity between P and Q? V plus V prime. And V plus V prime is clearly a measure of the rate at which elongation x changes with time. So dx dt essentially is V plus V prime. Dx dt is V plus V prime. So I end up getting K V plus V prime equal to m. Now V prime I already know as a function of time. My objective is to find V. We are done, because very clearly V then becomes m by k minus V prime. M by k minus V prime from this equation. V becomes m by k minus V prime. What's V prime? V prime is this. So this then is m by k minus gt plus t square by 2. Plus t squared by 2. That's the answer. So you would see that option A for this problem stands good. Alpha is given to be 1 and option A stands in good faith. So now if I have to just make a small remark on the problem, whether it was easy or difficult, you realize that there was nothing exotic about the problem. But then for sure, it was just a bunch of mixed things, and you had to learn how to sieve them apart at birth. And if you learned how to sieve them apart at birth, then you're all in place. So keep your mental nerves intact. Problems that appear in this exam are not difficult, but they sometimes just look different. That's the whole idea. And if you can keep your nerves when you encounter a problem that just looks different, then you are all set. Yes or no? Right? You feel comfortable with whatever I've communicated? Right. So this problem certainly was within reach. It wasn't a difficult problem, but it was a different problem. Maybe not one of those regular textbook problems, but for sure it involved concepts that were benign and simple. Very shortly, catch you with the next problem. Bye-bye. Problem, which is a very typical mechanical situation. We are given a rod P with a ring at the end, small ring at the end. The rod P is of length 1 meter, and there is a rod Q, a longer rod Q, which passes through the ring at C, right? And the rod Q is known to be hinged about P. The rod Q is known to be hinged about B. It can swivel this way. And correspondingly, the rod P, which is of 1 meter length, will also rotate in a plane, in the same plane, and again it's hinged at A. It will rotate about A. Now if C is the end, and what we seek to find is the distance between A and B given the variation of phi with theta. This is the angle phi which will vary, this is the angle theta that will vary, while P and Q both swivel about A and B respectively. Now, given this variation of phi with theta, we want to be able to find the distance between points A and B. Now, realize that C is one end of the rod P of length 1 meter. And it's fixed at A. It's fixed at A. Very clearly, the end C will move in a circle centered at A and of radius 1 meter. The end C will move in a circle of radius 1 meter centered at A. So the locus of C, while both the rods swivel, the locus of C, the locus of the end C is a circle centered at A and of radius 1 meter. Clear? Now you see, say at some instant of time the rod Q makes an angle phi, right? Then C could have had two positions. This could be one position of C, this could be the other position of C, the end of the rod P, right? This position of C will give me one value of theta, and this position of C would give me another value of theta. That means in general, for a given phi, you're going to see two values of theta, which is what you see in the diagram, right? Now, evidently, this phi would become a maximum. This phi would become a maximum if this rod Q becomes a tangent to the circle, isn't it? This phi would reach its greatest value when the rod becomes a tangent to the circle. That means this would be the case when this phi would have become a maximum. And when has phi become a maximum? When theta becomes 60 degrees, right? So when this angle is 60 degrees, phi is phi max. Yes or no, right? Now, of course, the problem is very simple. This is 60 degrees, this is 90 degrees. Very clearly, AB, the distance between the two fixed points, is 1 sec 60 degrees. 1 sec 60 degrees, which is clearly 2 meters. The distance between A and B is 2 meters. Would you call this problem difficult? It might give a difficult appearance. Once again, it might give a difficult appearance. But if you mentally get used to encountering different problems, then, it will not look like a difficult problem at all. So it's all about getting mentally conditioned to situations that look different. So this is one instance. Thank you so much. We'll catch you in some time. Bye-bye. So another problem. We have a system as shown. We have a tank of length 4 meters, of height 4 meters. And it's filled with liquid of density rho. This is a liquid of density rho. And the mass of the liquid is 5 kgs. Except for a portion of this volume, which is occupied by a sphere, this sphere, which is occupied by a sphere whose density is 2 rho and the mass of the sphere is 2 kgs. P is the bottom of this tank. Now for this system comprising the mass of the liquid and the sphere, we want to be able to compute the height of the center of mass above P. This is what we want to be able to do, right? Now, realize that this sphere of density 2 rho and mass 2 kgs could be looked upon as a sphere in the same volume. If I had liquid of density rho, then its mass would be 1 kg, half the mass? Yes or no? This total density is 2 rho. If I had imagined this to be density rho, synonymous with the density of the liquid, then the mass of this volume would have been half the mass of the sphere. That means it would have been 1 kilogram. This would have been 1 kilogram, the mass of the sphere, plus another 1 kg placed at the center of the sphere. Another point mass of 1 kg placed at the center of the sphere. Yes or no? Realize that this sphere of density 2 rho and mass 2 kgs could be imagined to be composed of two discrete entities. One, a sphere of density rho, that means same as that of the liquid, and therefore its mass would be half the mass of the sphere, and a mass 1 kg, the remaining mass 1 kg placed at the center of the sphere. This is what I could imagine this to be. Yes or no? Now, what I then do is, this part I take and plug it here, which gives me a uniform liquid. This entire tank, right? If this portion is replaced by this, then this entire tank would be a liquid of density rho, and the mass of the liquid now would not be 5 kgs, 5 kgs plus another 1 kg, that makes it 6 kgs, right? Plus this point C, where the center of the sphere originally was, this C, where the sphere originally was, there is a point mass 1 kilogram. Yes or no? So this sphere has been replaced by two things. One, that completely flushes with the volume of the liquid, right? Plus a point mass 1 kg at the center of the sphere. How about it, right? So what we have is a tank. Essentially, which is filled with a liquid of density rho, and mass equal to 5 kgs that originally was, plus another 1 kg because of this. That is 6 kgs of the liquid filling up 4 meters plus 3 meters above the base, 3 meters above the base, that is at C. There is a 1 kg mass. 3 meters above P, 3 meters above P, there is a point mass which is 1 kg. Yes or no? M2 which is 1 kg. And now it's very simple. I have to find the center of mass of the system above P. Right. For the liquid, what's the total mass? The total mass is now 6 kgs. 6 kgs. Right? Into the center of mass of this liquid would be 2 meters above the base, because the total length or height of the liquid is 4 meters. It's uniform, and the center of mass of the liquid alone would be 2 meters above P. So mass into how much above P? 2 meters above P plus. This 1 kg mass is 3 meters above P. So 1 kg into 3, right? M1 H1 plus M2 H2 divided by M1 plus M2. 6 kgs plus 1 kg. That is 7 kgs, right? That's the height of the center of mass above P. How about it? So that makes it 12 plus 3, 15 by 7. So height of the center of mass above P is 15 by 7 meters. Yes or no? This was, I think, a very ordinary problem, and it was easy to conceive everything that I have communicated. I would expect all of you who are appearing for the advanced exam, I would expect you to have done this problem right. This way or some other way, come what may, it was an easy to crack problem, right? Let's get on to the next one. Bye-bye. So, another situation. We have a trolley, and there is a smooth circular tube inside the trolley fixed with respect to the trolley. And the trolley is moving with a speed V, And at a certain instant of time, when the trolley is moving with a speed V, there is a particle, small particle of mass m. This is the particle of mass small m in the circular tube, right? That was at time t equal to 0. Now suddenly, brakes are applied to the trolley. Consequently, the trolley starts to decelerate. A is the deceleration of the trolley. That means its acceleration would be A leftwards. Its acceleration is A leftwards. That tantamounts to deceleration. Now, after a while, so if the trolley is decelerated, its speed would reduce to 0 at some instant of time. So the trolley comes to rest. And it's given in the problem that by the time the trolley comes to rest, this bead, this particle of mass m inside the circular tube would have swiveled by an angle theta, and it would have acquired enough velocity to reach the top of this tube. This is what is given, right? We want to be then able to find the deceleration A that the trolley was imparted. Now, we'll look at this problem in a frame of reference attached to the trolley. From the instant it starts to decelerate, that means having an acceleration A leftwards, we will look at everything in that frame of reference. So very clearly it's a non-inertial frame. Now look at this particle small m in the non-inertial frame. In the non-inertial frame, would you want to believe, that means in the trolley frame of reference, the mass m experiences mg downwards, Mother Earth anyways, right? There is obviously, there is a normal reaction also. There is also a normal reaction from the circular tube. There is a force that the circular tube exerts. And in addition, there is going to be a pseudo force on small m, ma to the right. There is going to be a pseudo force, ma to the right. Now, this normal reaction anyways. So, what I'm going to do is, I'm going to apply work energy principles for the particle going from A to B. We'll apply work energy principles for the particle going from A to B. Now, what are the various forces doing work? There is mg acting downwards. When the particle goes from A to B, mg is always acting downwards. There is displacement 2r upwards. So, what's the work done by gravity? Work done by gravity would be minus mg into 2r. Right? Now, what's the work done by the normal reaction? 0. Because, see, at all points of time, the normal reaction is along the normal from point to point, and the displacements are along the tangent to the tube. The displacements are along the tangent to the tube with respect to the tube. Yes or no? And therefore, the work done by normal reaction is very clearly 0. Right? Because the normal reaction and the tangential displacements with respect to the circular tube, they are perpendicular to each other. So, work done by normal reaction is 0. Now, there is pseudo force. Now, pseudo force does not act all the time. Pseudo force acts till the time the trolley comes to rest. After it comes to rest, very clearly, there is no more pseudo force. But then, in this entire journey from A to B, there is work done by pseudo force, but the work done by pseudo force is only till this extent, when the particle swivels by an angle theta. Now, pseudo force is acting horizontally, ma to the right, and in the direction of the pseudo force, there is displacement. When the particle goes from A to B, A to E, the pseudo force has acted to the right, and the displacement in the direction of the pseudo force is dE, which is r sine theta. So, what's the work done by the pseudo force? ma into r sine theta is the work done by the pseudo force. So, ma into r sine theta, that's the work done by the pseudo force. Right? And from E to B, there is no more pseudo force. The whole system has come, the trolley has come to rest. There is no more acceleration. There is no more retardation. And therefore, E to B, there is no more pseudo force. Right? So, from A to E, this is the work done by pseudo force. From E to B, the pseudo force does no work. So, in all, from A to B, this is the total work done by the pseudo force. And that must be change in kinetic energy with respect to the trolley. Initially, at this instant, right, at time t equal to 0, this particle also had a velocity v. What is its kinetic energy with respect to the trolley? 0. Initial kinetic energy with respect to the trolley is 0. Finally, when it just about reaches the topmost point B, the trolley is at rest, and the particle is also at rest. Again, the kinetic energy of the particle with respect to the trolley once again is 0. The kinetic energy in the trolley frame of reference for the particle reaching B is 0. So, 0 kinetic energy with respect to the trolley at A, 0 kinetic energy at the topmost point B with respect to the trolley in the trolley frame of reference. This is the total work done in the trolley frame of reference. This is gravity, this is pseudo force, and this must be total change in kinetic energy with respect to the trolley, final minus initial. Final is 0, initial is 0, difference is 0. Yes or no? This gives me very clearly a direct access to the retardation A produced or imparted to the trolley. A then very clearly, as you can see, is 2g by sine theta. A is very clearly 2g by sine theta. How about it? Make sense? All right. Let's move on to the next problem. Bye-bye. So this one problem on thermodynamics. Thermodynamics is always an easy to crack situation, and this one is no exception. So this one problem is about 4 moles of hydrogen at a temperature of 500 Kelvin. Out of this, 1 mole of hydrogen dissociates into atoms. 1 mole of hydrogen, when it's dissociating into hydrogen atoms, it is producing 2 moles of hydrogen atoms, right? Which is monoatomic, right? And the remaining 3 moles are remaining hydrogen, right? The dissociation energy involved in this is given to be 2000 calories, and the temperature subsequently of this mixture is found to be 100 T, and we want to be able to obtain the value of T, yes or no, right? Now this is about equating. The whole process is carried out under adiabatic conditions. So if it's carried out under adiabatic conditions, you would expect that the total internal energy of the system will remain preserved, yes or no, right? Now, what's the total internal energy originally? The total internal energy originally is 500, that is the temperature, into number of moles 4, into CV, which is 5R/2 for a diatomic gas. R is given to be 2 calories per mole per degree Kelvin, so this will become 5, yes. These many calories is the total internal energy initially. Where all does it get delegated? Into 2 moles of hydrogen atom with CV equal to 3 and temperature equal to 100 T, right? Plus 3 moles of hydrogen, 3 moles of hydrogen into CV, which is 5 into temperature 100 T. That's the internal energy of this hydrogen, right? Hydrogen gas. Plus there is 2000 calories of dissociation energy. Yes or no? Right? This is what transpires. We want to be able to calculate T. We want to be able to calculate T. Let's see how much is it. Very clearly, again, as you can see, let's simplify calculations. This gets cancelled, this gets cancelled, this gets cancelled. We have 6T plus 15T, that makes it 21T, equals 100 minus 20, which is 80. So the temperature of the mixture subsequently is 80 by 21 Kelvin. 80 by 21 Kelvin. Yes or no? The closest integer to T, the closest to 80 by 21 is 4 Kelvin. So roughly 4 Kelvins. So the integer closest to T is 4 Kelvin. So this was a very ordinary situation to deal with. Yes or no? Right? Okay. So this one problem is about a wedge of mass capital M placed on a smooth surface, and there is a small insect that starts to crawl along this quarter of a circle whose center is C and radius R. And this insect crawls with a constant speed V along this quadrant. This insect of mass M starts from here and it crawls at a constant speed V along this quadrant. Now, on the wedge, a force capital F is applied. And it's applied, and it's not a constant force, beg your pardon, it's a variable force. A variable force F is applied to maintain the wedge stationary at all times, right? We want to be able to find a relationship between F, V, and theta. This is what we seek to do in this problem, right? Now, when the insect has crawled by an angle theta with respect to the horizontal along the quadrant, speed V, realize that it would require at this point a centripetal force which is mv squared by r along the radial line towards the center C of the circle, right? And this mv squared by r makes an angle theta with the horizontal, right? So its horizontal acceleration is going to be mv squared by r cos theta, right? Now, if such is the case, what I could do is, on a system comprising capital M plus small m, I'll apply generalized Newton's second law. So the net horizontal force on the system is capital F. That must be equal to the mass of the wedge into acceleration of the wedge, which is 0, plus mv square by r cos theta, which is the horizontal So mass into acceleration horizontally of small m, which is mv squared by r cos theta. Yes or no? Right? So mass into acceleration horizontal of capital M, mass into horizontal acceleration of the insect. V square by r cos theta is the horizontal acceleration of the insect. Yes or no? And that gives me very clearly F equal to mv squared by r cos theta. So that's force, the variable force as a function of theta, given that the insect crawls down with a constant speed. Be very ordinary problem. See, the key to this problem was making sure that you didn't involve the normal reaction between small m and the wedge. That would have been an additional force to deal with. And since it was not even required by the problem even remotely, it was a good idea to look at a system that comprised capital M and small m and apply Newton's second law, generalized second law on the system horizontally. This is what we get, right? This was, I think, a sitter in a certain sense. If you didn't find this a sitter, you might want to go back to your mechanics and take a fresh look at things. Bye-bye. So now this one, another very basic problem in fluid mechanics. We have a tube which is filled with a liquid. And about this axis, this tube is given an angular velocity omega. And these are the heights of the free surfaces given, various dimensions offered in the problem, and we want to be able to calculate omega for this situation to occur, right? Now realize that the difference between this free surface and this free surface is h units, right? The difference between these two free surfaces, one end and the other end is h units. How much is h? Okay, now this you can see is 15 plus 10, 25 centimeters. This is 25 centimeters and this is 20 centimeters from the base. So this h is very clearly 25 minus 20, which is 5 centimeters, right? Now this limb moves in a circle of radius r, this limb. So r, as you can see, given in the problem is 10 centimeters. And we want to be able to calculate omega. Now, very direct result, this h and r, h is omega square r squared by 2g is the result that you may have encountered before. We'll take g as 10 for convenience. Very clearly, omega then is root 2gh, 2 into 10, and h, as you can see, is 5 into 10 to the power minus 2 meters divided by r square. R square is 100, so 100 into 10 to the power minus 4 meters squared. That must be omega, these many radians per second, right? How much does it turn out to be? Let's evaluate. This is 10 to the power minus 2. This will get cancelled with this. So 10, 10, 100. So that makes it 10 radians per second is the angular velocity. Now this, for sure, 100% a sitter for everyone who's ever read fluid mechanics. If you do not know this, again go back to the regular textbook and figure out what happens when a U-tube is rotated about a certain axis. This you must know. Or a vessel filled with liquid, what happens when it's rotated with a certain angular velocity, how the free surface assumes a parabolic trajectory, and what's the relationship between h and r for various points on a free surface. It is imperative, it is important that you know that result verbatim. This is that result, but get into the proof of that result so that any variation, any deviation around this could be independently handled in an exam-like situation. Bye-bye. We'll see you in some time. Now this one on geometrical optics, fairly simple. So what we have is a mirror, horizontal mirror say, and there is a source of light T. And there is a beam that is incident on the mirror, And this ray of light makes an angle theta equal to 37 degrees with the vertical. Theta equal to 37 degrees with the vertical. And subsequent to reflection from the mirror, it finds a spot S1 on a certain vertical wall, right? Now what is done is, the mirror is shifted up by 1 centimeter, the wall is shifted to the right by 1 centimeter. We want to find by what amount this spot on the wall would move up when the two situations get compounded. One, the mirror moved up by 1 centimeter, the wall moved to the right by 1 centimeter. By what amount vertically would S1 move? Now, more elaborate figure. This was the original position of the mirror. This was the source of light, the torch. There is this ray of light incident here. Now this angle is theta, so angle of incidence theta, angle of reflection theta, and this reflected ray settles here on the wall. Mirror moved up by 1 centimeter. So then, instead of P being the point of incidence, Q becomes the point of incidence, and reflection occurs at Q. Reflection occurs at Q. If the wall was not moved, this would have been the new spot, right? But the wall itself is moved to the right, so the ray of light traverses further, and this becomes the revised spot on the wall, S2. I want to find the vertical shift between S1 and S2. Clear? Now, very ordinary situation really, very simple. More than optics, it's geometry, and maybe junior level geometry. So this angle is theta, this angle will be theta, right? Alternate angles. If this is theta, this is theta, this is 90 minus theta, and therefore this will be theta, right? And this is theta, this will be theta. Yes or no, right? These are normals to parallel lines. So if this is theta, this will be theta. Clear? This length shift of the mirror is 1 centimeter. And do you realize that triangle SQR and triangle SQP are congruent triangles? Why? Why? Because this angle equals this angle. This is 90 degrees, this is 90 degrees, this is common to both, right? So very clearly 2 angles and 1 side. 2 angles and 1 side, so AAS condition, this is the common side, 190 degrees, 1 theta. So causes SQR and SQP to be congruent triangles. Therefore, if SP is 1 centimeter, evidently SR will also be 1 centimeter. How about it, right? So SR turns out to be 1 centimeter as well, right? Now, look at this. Let me call this S1, let me call this S1 prime, right? If the wall had not moved, this would have been. Realize R S1 prime, S1P. R S1 prime, R S1 prime, S1P is a parallelogram. Evidently, you know, this reflected ray and this reflected ray from both positions of the mirror would be parallel to each other, and this is parallel to the wall, right? The normal is parallel to the wall. So this is very clearly a parallelogram. So if PR is 1 plus 1, 2 centimeters, PR is 2 centimeters, and therefore S1 prime will also be 2 centimeters. S1 prime will also be 2 centimeters. Clear? This is 2 centimeters. Now, so there is already a vertical shift, 2 centimeters. Now there is an additional vertical shift, which is this. So the net vertical shift from S1 to S2 would be this 2 centimeters plus this additional amount. Now, this length is 1 centimeter. So this height, H you can see would be 1 cot theta. H would be 1 cot theta. Cot theta means cot 37 degrees. Cot 37 degrees is cos 37 by sin 37. That makes it 4 by 3. So H is 4 by 3. So what's the net vertical shift? The net vertical shift is 2 plus 4 by 3. Net vertical shift Vs is going to be 2 centimeters because of the mirror and 8 centimeters because of the wall, right? So 2 plus 4 by 3, 6 plus 4, 10 by 3 centimeters is the net vertical shift produced by the compounded effect of the mirror moving vertically up and the wall moving to the right. You can't come up to me and tell me that you couldn't solve this problem. The only way you couldn't have solved this is if you just got lost with things. If you had maintained mental clairvoyance, mental clarity, this problem would have been a sitter, and a sitter. Bye-bye. So this one situation about two lenses, one with focal length f1, another with focal length f2. This is their common principal axis, and there is a ray of light incident on lens 1, and it gets deviated by an amount delta. This ray of light runs parallel to the principal axis. And then it's incident on lens 2, and it subsequently gets deviated by the same angle, delta, by the second lens. Now the deviation, as you can see from this figure, produced by a lens is given by h by f. Tan delta is h by f. Delta is small because we are talking of paraxial rays. So the angle of deviation is roughly h by f produced by a lens, where what is h? H is the height of the point of incidence above the optical center. That means distance from the principal axis divided by the focal length of the lens. Now in this case, we need to check whether f1 is more than f2 or f1 is less than f2. Now the deviation very clearly produced by both lenses is the same. What's the deviation produced by this lens? It's h1 by f1. What's the deviation produced by this lens? h2 by f2. Yes or no? Right? So this gives us f1 by f2 is h1 by h2. f1 by f2 is h1 by h2, and very clearly if h1 is more than h2, as you can see, h1 is more than h2, that means this is greater than 1. Evidently f1 has to be more than f2. f1 has to be more than f2. So the focal length of this lens is more than the focal length of this lens. Simple, right? Right then, we'll catch you in a little while. Bye-bye. For you, really plain and simple problem. We have a LC circuit, inductor capacitor circuit, and the charge on the capacitor is related to current in the electrical circuit in the inductor, and is given by Q square by 2C is half Li squared for a certain situation, right? We want to find the time period of oscillation of this electrical circuit. Now, evidently, omega, the angular frequency of oscillation of the electrical circuit, is given by 1 by root LC. That's the angular frequency of oscillation of the electrical circuit. Can I find LC from this? Yes. What is LC? LC, as you can see from this circuit, is Q squared by I squared. Right? That's LC. Therefore, 1 by root LC, as you can see, is going to be I by Q. I by Q, current by charge. That's the angular frequency of oscillation of the circuit. And the time period then is going to be given by time period of oscillation of the electrical circuit is 2 pi by omega, which is 2 pi Q by I. That's the answer, right? And certainly, I expected everyone to be able to do this problem, right? I'm assuming you've got it right, and I hope it makes sense to you. Bye-bye. Catch you in a little. So this next problem is based on thermal expansion. We have a rod of length L at a certain temperature, and the coefficient of linear expansion for this rod is given as 10 to the power minus 3 per degree centigrade. Now, we need to figure out the change in length of the rod. We need to figure out the change in length of the rod, given that the change in temperature is 1000 Kelvin. Now, would you mind believing that alpha is 1 by L dl dt, dl dt, right? dl by L is fractional change in length, dt is the change in temperature, right? That's the definition of alpha, 1 by L dl dt. And this would lead us to dl by L is alpha dt, right? When I integrate both sides, then this would give me log of final length, say L changes from L1 to L2, right? So this would give me log of L2 by L1. L1 is the initial length, that's alpha into change in temperature, which is delta T, right? But alpha into delta T is 1. See, 10 to the power minus 3 into 10 to the power 3, that's 1. So this gets us to L2 equals E times L1, right? L1 is capital L, so L2 is roughly 2.7 times capital L, right? So very clearly, the final length is more than twice the initial length, more than 2.5 times the initial length. So you would see that options A and B are eligible for this problem. Very simple. It's based on a direct definition of alpha, coefficient of linear expansion. You know, this one chapter is a very easy chapter, and generally speaking, for some reason or the other, students either don't even go through it, it's not even covered properly by most people, and therefore, you know, even simple problems on this chapter sometimes go ignored, unattended, and people lose marks on sitters. All problems in this chapter would literally be sitters. So don't ignore this chapter. Thermal expansion is easy and within reach. So this is low-hanging fruit, and you must make sure that you read up this chapter properly. Even if you go through some simple examples of this chapter, that would suffice. Trust me, in these many decades, I have never encountered any exotic problem on this chapter appearing in any exam. So therefore, take advantage of this fact and get set. Thank you. Bye-bye. This one problem is about a model of an injection, and there is an orifice at the end of the injection, and a force F is applied, on this piston, so that water is or whatever liquid there is ejected with a velocity v, right? And the entire experiment is performed in gravity-free space. We need to check the following options. The first option is the force would be proportional to v squared, the square of the velocity of a flux. The power required is going to be proportional to v cubed. We need to check this. Time taken to empty the tank will be proportional to v to the power minus 1, and work done by this force will be proportional to v square. We need to check all of this, right? Now, very simple. Applying Bernoulli's theorem across the top of this surface, that means this free surface, and at the exit, and both are at atmospheric pressure. So then the difference in pressures between this point and the exit is only F by A prime. A prime is the area of cross section of the piston. F by A prime. I'm applying Bernoulli's theorem between this free surface and this exit, right? Both are at the same pressure. The only difference in pressures at this point is the pressure because of the force F applied on the top of the piston, plus half rho is the density of the liquid, and v prime squared, and that must be equal to the same thing here, half rho v squared. The g term is not present, gravitational g, because it's a gravity-free space. So there is no potential difference between this topmost point and the point 2. Now again, owing to continuity principles, if v prime is the velocity with which this falls down, and A prime is this area of cross section, then from continuity principles, A prime V prime must be equal to A into V. And it's given that this A is much smaller compared to A prime, and therefore V is much larger compared to V prime, right? The velocity with which this piston falls down is much smaller compared to the velocity of a flux of the liquid from the injection. And therefore, what we could do is we could ignore this term for all practical purposes. V prime is really small, and therefore it could be ignored, which then gives us F equals rho a prime by 2 into v squared. Very clearly, F is proportional to v squared. So option A is correct. The power very clearly is force into velocity. So force into v prime, actually, force into v prime, right? Now, again, look at v prime. V prime is AV by A prime. V prime can be written as AV by A prime. AV by A prime, right? And check this out. Force proportional to v squared into v, that means v cubed. That means power required to do this is proportional to v cubed. So that makes option B also eligible, right? Now again, we are maintaining this constant A into V, and evidently then, you can see from here the time taken to empty the tank. Time taken to empty the tank would be the total volume of the tank. Total volume of the tank divided by the volume flow rate. The volume flow rate is A into V. A into V. So very clearly, T is proportional to V to power minus 1, which is also true, right? Now work done to empty the tank by this force. Work done very clearly would be force into, let's say, this displacement. This is the displacement S. And force is proportional to V squared. This F, as we have already witnessed, is proportional to V squared. So work done to empty the tank is also proportional to V squared. That makes option D also eligible. So for this problem, which is again a simple problem, direct application of Bernoulli's theorem for a very ordinary, very regular situation, pretty much within your reach. Work done to empty the tank is proportional to V squared, as you can see. Thank you so much. Bye-bye. So again, a very routine problem on electrostats. Direct application of concepts that you may have already learned. We have in the xy plane electric field given by xi cap plus yj cap, obviously a variable electric field. At a point x comma y, the x component of the electric field is x units, the y component of the electric field is y units. And it's also given that the potential at a point 2 comma 2 is taken to be 0, right? Now given this data, we want to be able to explore the following options A, B, C, D. Nature of the equipotential surfaces, then potential at any point. These are various options that we will evaluate, right? So first of all, equipotential curves. That means let me find out potential as a function of x and y. Potential as a function of x and y. Now, if a particle is at x comma y and it is moved from x comma y to x plus dx and y plus dy under the influence of this electric field, then the work done by the electric field is going to be given by E dot, the displacement. Displacement in the x direction is dxi cap, displacement in the y direction is dy j cap, right? Yes or no? And this must be from, that means, I'm moving the particle from x comma y to x plus dx comma y plus dy. That means displacement in the x direction is dx, displacement in the y direction is dy. And this has resulted in change in potential dV. So work done by the electric field is negative of the change in potential, right? That's by definition of potential. Now, what does this turn out to be? E, if I plug in as xi cap plus yj cap, then this will become like a x dx on taking the dot product plus y dy, right? That's minus dv, minus dv. So minus dv is x dx plus y dy, right? Let me integrate both sides. Or what you could do is, if you are comfortable with algebra of differentials, then this you could write as half of dx squared plus y squared, right? That's minus dv. On integrating both sides, I end up getting minus v is, and let's say a constant of integration, c, from both sides. That's half of x squared plus y squared. That's half of x square plus y square. And then this gives us an opportunity to know V as a function of x and y, potential as a function of x and y. How does one obtain the value of C? How does one obtain the value of C? At x equal to 2, y equal to 2, V is 0. So put x equal to 2, y equal to 2, and V as 0. So you end up getting C equal to 4 plus 4, 8, 8 by 2, 4. So that gives me C equal to 4. On using this boundary condition, at x equal to 2, y equal to 2, V is 0. So I end up getting C equal to 4. 4 plus 4, 8 by 2, 4, V is 0. Right? At x equal to 2, y equal to 2, V is 0. That gives me C equal to 4 using this boundary condition. So C is 4. That gives me 4 minus V, that's the left hand side, into this 2, that's equal to x square plus y square. Yes or no? Does it make sense to you? Now, what does this represent? X square plus y square equal to 2 into 4 minus V for a given V. For a given V. When I talk of a given V, that means I'm talking of a set of points having the same potential, right? For a given V, the left hand side would be a constant, and x squared plus y squared equal to a constant would give me a circular regime. A circle with center 0, 0. X squared plus y squared equal to a constant will give me a circle with center 0, 0. So, when I talk of equipotential surfaces, I'm selecting a relevant value of V, a constant value of V, any value of V that makes sense. Plugging into this, then x squared plus y squared is going to be a constant, and this would represent a circle. So, for different values of V, I get concentric circles with center 0, 0, and with different radii, obviously. So, this option A is wrong. Equipotential curves are concentric circles with center 2, 2 is wrong. Equipotential curves are concentric circles with center 0, 0. Right? So, option A is obviously ruled out. Potential at any point cannot exceed 4 units. Yes, indeed so. Indeed so. Because if V is more than 4 units, this will become a negative number, but x squared plus y squared cannot be negative. So you can't have real xy such that x squared plus y squared is a negative number. So potential at any point cannot exceed 4 units. That's true. That's true. B is true. Work done in moving a charge q slowly from AB to BA. Work done in moving a charge q slowly from AB to BA is 0. Yes. Because AB and BA would lie on the same circle, isn't it? X squared plus y squared equal to some constant, which is the equation of an equipotential curve. Equipotential curve for this description. So obviously if AB satisfies this condition, BA will also satisfy this condition. That means AB and BA lie on the same circle centered at the origin. AB and BA lie on the same circle centered at the origin, and therefore the work done in moving a charge q, a test charge q from AB to BA is 0. Same circle means same equipotential curve. That means potential difference between points AB and BA is going to be 0. So the work done is going to be 0 when I cause a test charge to move slowly from AB to BA. Yes or no? So option C is also correct. Because AB and BA belong to the same equipotential circle. Same equipotential circle. If AB satisfies this condition, BA will also satisfy this condition. So option C is correct. Right? Now, one thing that you can see is the radius of the circle, right? The radius of this equipotential circle, R, is square root of 2 into 4 minus V. Do you see that? Do you see this? Right? Very clearly, if V is increasing, R is decreasing. If V is decreasing, R is increasing. That means as the radius of the circle increases, V is decreasing. As the radius increases, V decreases in this case. Yes or no? As the radius increases, V decreases. That means as I take larger and larger concentric circles, I fall under smaller and smaller equipotential curves. Yes or no? Is that okay? Now, I need to check all points lying on the curve x plus y equal to c, where c greater than 4 have negative potential. Hey, let's see that. Let's explore the truth of this statement. This last statement, let's check this out. See, there is a circle equipotential curve, and this is a circle on which 2 lies. This is a circle on which 2 lies, and at this point the potential is 0. So at all points on this circle the potential is going to be 0. Yes or no? Right? That means this is a circle with v equal to 0, and if v is 0, radius, as you can see, is 2 root 2. The radius of the circle is 2 root 2, isn't it? If v is 0, radius is 2 root 2, as you can see. Now, we are talking of a line x plus y equal to c, where c is greater than 4. Let me look at a line x plus y equal to 4. Now, x plus y equal to 4 would be a line passing through 2, 2. Yes or no? X plus y equal to 4 would be a line. This is a line. X plus y equal to 4 is a line passing through 2, 2 and is tangential to this circle centered 0, 0 and passing through 2, 2. It's a tangent to this circle with 0 potential, right? Now, if I select a line x plus y, equal to c, where c is greater than 4, do you realize that? X plus y equal to c, where c greater than 4 will be a line parallel to x plus y equal to 4. That means for c greater than 4, I am moving further and further away. Yes, that means x plus y equal to c, where c is greater than 4, would be a line passing through a circle with radius more than the radius of the circle, right? Therefore, if I go on increasing the radius of the circle, the potential decreases. Yes or no? And this circle is 0 potential. This will pass through a circle. This will be a tangent to a circle with the radius more than 2 root 2. And if the radius increases, the potential decreases. Yes or no? So x plus y equal to c, where c greater than 4, if I select all points such that x plus y equal to c, where c is greater than 4, then those points will lie on circles more than the radius of the circle. That means bigger than the circle. And the bigger the circle gets, the potential decreases. Therefore, if this is 0 potential, then circles larger than this will have negative potentials. And that will cause option D to be eligible. All points lying on x plus y equal to c, c greater than 4 have negative potential. Because x plus y equal to c, c greater than 4 would be about circles larger than the 0 potential circle. And the larger the circle, like I said, the greater the radius of the circle, smaller the potential. If this is a circle with 0 potential, circles larger than this would have negative potentials. And that makes option D also eligible. So for this problem, B, C and D are appropriate options. So this again was not a problem beyond reach by any standards. And the only option that could have bothered you was D. As far as B and C and evaluation of A was concerned, I personally would believe that if you have read your electrostats properly, even from a regular textbook, and have heard your teacher properly, then this problem should have been within reach. Problem part D could have posed a problem to some students, but otherwise I feel this was a problem that should have been attempted. I would not know whether I should call it a sitter, maybe slightly more than a sitter, but certainly not an advanced problem, simple problem otherwise. Thank you, bye-bye. The next one again is about evaluating the voltage sensitivity of a voltmeter, a DC voltmeter. A galvanometer, as you know, could be converted into a voltmeter, and the galvanometer current can be given by delta V by Rg plus R, and N is the number of turns, B is the magnetic field, A is the area, Ig galvanometer current. All of this, product of this is proportional to the deflection of the needle that measures the current, right? And C is the stiffness constant. C is the stiffness constant, a torsional constant of that needle, right? Now, sensitivity is defined as theta, the deflection of the needle, per unit volt measured, per unit volt measured. Now, theta by delta V from these two, you would get as NBA by C, 1 by Rg plus R. Now, this then is the voltage sensitivity of a voltmeter, a galvanometer converted into a voltmeter. Now, we need to explore these four options. Voltage sensitivity of a DC voltmeter can be decreased by 1. Increasing resistance for conversion. If I increase Rg, then obviously sensitivity would decrease. Yes or no? If I increase Rg, this sensitivity, voltage sensitivity would decrease, and therefore option A is right. B, increasing torsional constant C. Yes. If I increase C, again this sensitivity would decrease, so B is also right. C, if I increase B, then sensitivity would increase, so this is not right. C is not right. And then option D, by decreasing N. Obviously, if I decrease N, this expression will decrease in value, and therefore option D. Direct formula, much ado about nothing. This one problem, obviously, I didn't think it was required to deliberate too much on this problem, but these problems they throw up in examination so that you could score marks. Some reason or the other, again, I would not know why, but most students end up ignoring this easy portion, the ammeter, voltmeter, converting a galvanometer into ammeters and voltmeters, and understanding those basic rudiments related to these things, somehow ignored by students. They don't find it too exciting, and they end up not reading this, and they lose some low-hanging fruits. So don't lose this low-hanging fruit. All's there for you. Bye-bye. Thank you.